गाड़ी में
घोष सर, आप कुछ अपने एक्सपीरियंस शेयर कर सकते हैं?
हाँ,
सभी जगह आप कुछ अपने एक्सपीरियंस शेयर कर सकते हैं जब तक नहीं चालू होता?
आ गए ना, वाइस चांसलर सर हैज ऑलरेडी अराइव्ड।
जी जी सर।
आगे सामने मैं देख सकता हूँ, बैठे हैं।
हाँ,
संजय जी सामने बैठे हो।
अरे सर,
Dr.
Yakmi sir has also joined us from the Department of
Yes,
Technology.
yes.
Okay, sir. So you are welcome, sir.
Yeah, thank you.
So we are starting programs. Which is sir, Verma sir, can we start, sir? सर शुरू कर दें सर?
उनका कांटेक्ट चला।
जी हाँ, समय हो गया, प्रारंभ कर सकते हैं।
सर, गुड मॉर्निंग सर, गुड मॉर्निंग सर।
गुड मॉर्निंग, सभी को नमस्कार।
नमस्कार।
Happy Science Day.
Sir, Professor Ghatak and Professor Yakmi both have joined, sir.
Morning, Golu. Dr. Katari here is from Jabalpur.
Oh, you are welcome, sir. You are welcome. Okay. So we are starting this program. So
सर, आप
good
कुछ
morning to
अपने
one and
एक्सपीरियंस
all
शेयर
on
कर
this
सकते हैं?
historic day today, and I welcome you
आप
all
कुछ
to
अपने
this
एक्सपीरियंस
webinar.
शेयर कर सकते हैं जब
The
तक नहीं
chief
चालू
guest
होता?
of today's webinar, Professor Keshalal Verma, our Honorable Vice Chancellor of Pandit Ravi Shankar Shukla University, Raipur. Fortunate to have with us as guest Sir Ajoy
Yeah,
Ghatak.
thank you.
So we are starting programs. Which is Verma sir, can we start, sir? Professor Yakmi from Bhabha Atomic Research Center.
जी हाँ, समय हो गया, प्रारंभ कर सकते हैं।
Respected teachers, faculty members, our dear students, and all the participants, because participants have joined not only on YouTube, and not only on Google Meet, they have joined on YouTube also. Because there is an upper limit of 200 on this Google Meet, so they are preferred to join on YouTube. All the participants who are passionate for science, technology, and innovation. So we are starting this program. I am Professor Sanjay Tiwari. So
सर, आप कुछ अपने एक्सपीरियंस शेयर कर सकते हैं?
I welcome you
आप
all
कुछ
to
अपने
the
एक्सपीरियंस
webinar.
शेयर कर
The
सकते
day
हैं जब तक
has
नहीं
really
चालू होता?
webinar, Professor Keshalal Verma, our Honorable Vice Chancellor, International Authority on Optics, is today going to teach us Raman effect on this National Science Day. He will speak on Raman effect and fiber optics revolution. Professor Ghatak, as you know, the February 28 holds a special place in history, as on this day, India's prominent scientist, Bharat Ratna Sir Chandrasekhar Venkat Raman, discovered the Raman effect in the year 1928, and later on, in the year 1930, he won the Nobel Prize as the first Asian to win a Nobel Prize. And every year, this day is celebrated to mark the great discovery of Raman, and it is celebrated on National Science Day. The day is celebrated to mark the importance of contributions made by scientists towards the development of our nation and the world as a whole. And the purpose is also to create awareness about the role of science in society. And I think that Swami Vivekananda ने 1898 में कहा था कि भारत को अगर एक विकसित देश राष्ट्र बनना होगा, ऐसा सीवी रमन साहब ने इस चीज को सोचा, और उसी प्रकार से उसी दौरान आप देखें तो 1930s के बीच में इंडिया मेड द मैक्सिमम कंट्रीब्यूशन इन साइंस एंड टेक्नोलॉजी. So the theme of this National Science Day is Future of Science, Technology and Innovation, Impact of Education, Skill and Work. It's very, very important topic. So before starting this program, I invite our Honorable Vice Chancellor, Professor Keshalal Verma sir, for his blessings on this science festival. Professor Verma sir.
He has to unmute. Professor Verma.
Okay.
Chief Speaker of this national webinar, हमारे साथ जुड़ते हैं, हमारे शिक्षकों को, हमारे विद्यार्थियों को मार्गदर्शन देते हैं। यह ऐसा अवसर है जब हम उन महान वैज्ञानिकों को बात करके उनकी जो कंट्रीब्यूशन है, उन्होंने जो योगदान दिया है विश्व स्तर पर उनको याद करते हैं। और यह अवसर भी है कि हम वैज्ञानिक सोच को आगे बढ़ाने के लिए और वैज्ञानिक उन्नति के लिए कितना कर चुके हैं, आगे क्या हमें करना होगा, इस पर भी एक अवसर आता है जिस पर हम विचारें। अगर ऐसे कार्यक्रम में हमारे जो विद्वान साथी जुड़ते हैं तो मुझे बहुत ही खुशी होती है। विश्वविद्यालय परिवार की तरफ से पुनः आप सबका मैं विशेष रूप से अभिनंदन करता हूँ, स्वागत करता हूँ। और हमारे महान विद्वान प्रोफेसर अजय घटक का मैं विशेष रूप से आभार भी व्यक्त करता हूं कि उन्होंने हमारे साथ जुड़ के हम सबको मार्गदर्शन करने के लिए उन्होंने अपनी सहमति दी और हमारे साथ जुड़ रहे हैं। हमारे साथ बहुत सीनियर वैज्ञानिक साथी भी जुड़े हुए हैं। मैं देख रहा हूं नाम, मुझे बहुत अच्छा लग रहा है। और इस अवसर पर मैं आप सबको विज्ञान दिवस की पुनः बधाई देता हूं और आप सबको इस कार्यक्रम की सफलता के लिए बहुत बहुत शुभकामनाएं व्यक्त करता हूं। इसी तरह हम जुड़े रहेंगे और अपने इस वैज्ञानिक सोच को और वैज्ञानिक इन्वेंशन को आगे बढ़ाते रहेंगे। नमस्कार, जय हिंद।
सर आपका बहुत बहुत धन्यवाद, आपकी शुभकामनाओं के लिए, आपके संदेश के लिए। और आपका हमेशा ही मोटिवेशन हम लोग के साथ है कार्यक्रम आयोजित करने में। इसी श्रृंखला में एक कार्यक्रम हम लोगों ने 17 मार्च को भी आयोजित किया है डॉक्टर याकमी का, उसके डिटेल्स आपको शीघ्र ही भेजे जाएंगे। अब मैं हमारा पब्लिक आउटरीच सेंटर जो लगातार इस प्रकार के कार्यक्रम करवा रहा है, उसके डायरेक्टर प्रोफेसर कल्लोल कुमार घोष सर से मैं निवेदन करूंगा कि इस शुभ अवसर पर, राष्ट्रीय विज्ञान दिवस के अवसर पर अपना संदेश हम सभी को प्रेषित करें।
You are muted. आप muted हैं।
वो सर
Yes. Good morning, sir, and good evening to Professor Ajoy Ghatak, sir.
Yes.
Happy National Science Day. Respected our patron, Professor K.L. Verma, sir, inspiration of this program, and a very distinguished scientist, and we are lucky, Professor Ajoy Ghatak. He is joining from United States of America, and of Pandit Ravi Shankar Shukla University, I must say, Professor Jatindra Yakmi, sir, the coordinator of this program, Professor Sanjay Tiwari, sir, Registrar, Professor Girishkant Pandey, and the many faculty members of our university as well as the affiliated colleges, and most important, the brand ambassador of New India and brand ambassador of Chhattisgarh, all the young scientists of this area. I deem it a great, really a pleasure and honor to be part of this very historical event. Every year we, Pandit Ravi Shankar Shukla University, organize this National Science Day. And you all know that today we are remembering the great achievements of the Indian scientists as well as this great teacher, scientist, Professor C.V. Raman. And particularly this year, it has a tremendous impact because during this pandemic period, the Government of India, Department of Science and Technology, they have chosen a very important theme, that is the future of science, technology and innovation. And it is impact on the education. You all know that education is the most important part, and the skill development. We need now the skilled worker, because always we need, there is a transformation of science to technology and then technology to innovation. And really I must thank Professor Sanjay Tiwari because he has chosen the correct person. Because you know that Professor Ajoy Ghatak is a celebrated physicist, and you all know that Raman effect, we all know scattering of the light, everything we know. But what is the most important thing is that use of that Raman scattering for the recent development of optical fibers and everything, optics, everything is based on this Raman effect. So this is actually true transformation of the science, technology, and you can call it the innovation. And we all know that without innovation, no countries can achieve this sustainable development and prosperity. Under this public outreach center, we do organize such type of program regularly, and I think a few years ago also Professor Ajoy Ghatak was also here. Professor Acme is also here. We organize all these programs under the dynamic leadership of our patron, Professor K.L. Verma. And lastly, I take this opportunity to place on record our gratitude to our Honorable Vice Chancellor. He always motivated us, Dr. Sanjay Tiwari, and all the faculty members for academic excellence and holistic development of the university. So I, on behalf of this Public Outreach Center and on behalf of Pandit Ravi Shankar Shukla University and Electronics Department, I again welcome Professor Ajoy Ghatak sir and Professor Yakmi and other professors, some professors from Jabalpur and other part, and large number of participants are attending through the YouTube, and I hope that really we will enjoy all these lectures. And really, again, I must congratulate Professor Sanjay Tiwari and his team for organizing this National Science Day, this 28th February. Thank you very much. Thank you, sir.
Thank you, Professor Ghosh, for your kind message and your blessings. Everyone knows Professor Ghatak. Anyone who has worked or who knows optics, he knows Professor Ghatak, because he has become synonym for optics or photonics or optical electronics. Professor Ajoy Ghatak is fellow of Optical Society of America, and he was former professor at IIT Delhi and currently Nasi Meghna Saha Distinguished Professor. And basically, he's a true innovator who has dedicated his life to the development of optics education in India and across the globe. He is the recipient of many, many awards, and these awards are a fitting testament to his passion for optics education and research in fiber optics and quantum mechanics. We organized his lecture during the International Year of Light in the year 2015. He was kind enough to visit our campus, and he is honored with various awards like CSIR Bhatnagar Award for Outstanding Contribution in Physical Sciences, SPY Educator Award for Unparalleled Global Contribution to Fiber Optics Research, OSA Esther Hoffman Weller Award, OSA Amita Day Award for the lifelong research contributions and dedicated service to the optical community, and ICO Galileo Award. And most recently, he received the 2020, it was a very, very prestigious award, Sang Soo Lee Award from South Korea, and he was awarded from Optical Society of America for his seminal role in the development of fiber optics and guided wave photonics, and for pioneering optics education across the globe. And Professor Ghatak nurtured the fiber optics across the globe and published extensively in the area of optical waveguides and quantum well structures. And his methods have been used by many researchers. Even our lab we are running an MTech program in optoelectronics and laser technology, and we are using his methods in our lab also. And all you know, क्योंकि उनकी किताबें जो है कैम्ब्रिज ऑक्सफोर्ड से लेकर स्टैनफोर्ड हर जगह जो है ऑप्टिक्स फाइबर ऑप्टिक्स एंड ऑप्टिकल इलेक्ट्रॉनिक्स ऑल आर सो पॉपुलर बुक्स एंड दे आर ट्रांसलेटेड इन many foreign languages as Chinese, Persian and others. And today we are very excited because we are going to on Raman effect and fiber optic revolution. And there is similarity also. For Professor Raman was born on 7th of November and our Professor Ghatak was born on 9th of November, 2 days after Professor Raman. So without taking more time, I invite Professor Ghatak for his talk, Raman effect and fiber optics revolution. Professor Ghatak, sir, please, sir, start your talk.
Thank you. Thank you, Professor Tiwari. Can I present my slides?
Yes, sir.
What should I present? Your entire screen or window?
Window, sir.
Window. Okay. Can you see?
No, sir. No, it's coming now. Yeah.
Coming.
Yeah.
Pura.
Slideshow mode में नहीं है. Slideshow mode.
So फिर window full screen कर दीजिए sir. Window में आता है full screen कर दीजिए.
कर दिया मैंने.
It's not visible, sir.
आएगा एक सेकंड लगता है उसको.
Has it come now?
No, not yet.
अच्छा मैं दोबारा करता हूँ.
Yes.
Just 1 second. Okay, I started. A window or entire screen? Window.
No, entire screen, entire screen,
Entire कर दीजिए सर।
entire screen.
Entire screen.
Yeah. Entire.
Okay. No. नहीं, विंडो होना चाहिए, विंडो पूरा। Just 1 second. Can you see now?
No, sir, no, sir.
Not it, sir.
Coming.
आ रहा है।
आ गया?
But you make it full screen.
Full screen, sir.
Slide.
Yeah, it's okay. It's for us.
Slide is showing, but you make it full.
I am now in the full screen.
No.
It is not appearing.
Slide flow. You have to click on
सर
the
पावर पॉइंट को आप पहले फुल स्क्रीन कर दीजिए सर,
कर दिया मैंने फ्रॉम।
और
ये
इसके
कर
बाद पावर पॉइंट में आप ऑल्ट और टैब प्रेस करेंगे तो आप इस स्क्रीन पे आ जाएंगे। ऑल्ट एंड टैब।
टैब कौन सा है?
Enter.
वैसे स्क्रीन आपका आ रहा है बट इट्स विजिबल टू सम एंड बट नॉट टू ऑल आई थिंक।
No.
लेकिन यहाँ तो
For
full
me,
screen
it's
मैंने
visible,
दिखा
sir.
दिया।
All slides are here visible.
Now
You are trying to press. We can see. Now press it. Yes. Press होने के बाद ही लगने लगता है।
Hello.
अच्छा, can you see the fiber optics revolution slide? No.
Yeah, it's fiber optics revolution, sir. It's visible.
अभी आ रहा है। Just give 1 second.
You are present. इसमें तो लिखा है you are presenting.
Yes. Sir, give 1 second because these things take 1 or 2 seconds when you alter something.
अच्छा, let me cancel the presentation.
हाँ सर, रीस्टार्ट करें।
Window. Okay, once more. Okay. Can you see the fiber optics revolution?
Yes, sir.
Yes.
Yeah, it's visible for us.
It has not yet come.
No, the same frame is there, but not full screen.
तो मैं PDF भेज दूं आपको?
संजय आप
तिवारी साहब,
अनम्यूट हो जाओ। हाँ
माइक में। हाँ सर, PDF पे दीजिए इसका जो है।
आप चला दीजिए ना तिवारी साहब।
Can you see the full screen? No.
No.
पीपीटी प्ले करेंगे तब भी आ सकता है सर फुल स्क्रीन।
ओहो।
पीपीटी में F5 कर देंगे तो सर फुल स्क्रीन होगा।
हाँ। नहीं सर, पीपीटी प्ले करेंगे ना पीपीटी तो फुल स्क्रीन आ सकता है।
Present now. Your window. Oh.
Let's select the PPT.
ठीक है, ये तो कभी नहीं होता है। Just 1 second. Present now, cancel. Present now, a window. शेयर करना ना।
हाँ, शेयर। यस,
आ रहा है?
आ गया।
सर YouTube में स्क्रीन आ रहा है आपका?
यहाँ भी आएगा
सर। यहाँ पे फुल स्क्रीन नहीं आ रहा है, लेकिन वहाँ पे तो पीपीटी दिख रही है ना। You can continue.
Sir, please click F5 button.
हाँ, F5 बटन पेट किया।
अब पावर पॉइंट आपको दिख रहा है सर। अब पावर पॉइंट में क्या करिए आप, कंट्रोल एंड टैब को आप प्रेस करेंगे।
टैब कौन सा है? इसमें लिखा है FN, कंट्रोल ऑल्ट है, टैब, अच्छा कंट्रोल टैब
नहीं, ऑल टैब, ऑल्ट एंड टैब।
आ गया? नहीं आया।
नहीं सर,
ये
कुछ
ऑल्ट
दिख रहा है, यूट्यूब पे दिख रहा है आपका, कुछ सिस्टम पे दिख रहा है ये, मतलब यूट्यूब से कहते कि देयर इट इज विजिबल।
यूट्यूब पे फुल स्क्रीन आ रहा है, तो यूट्यूब पे देख लीजिए।
हाँ सर।
Sir, if you click on the
He can start. ऐसे ही
I can you see on YouTube the full screen?
हर टीम फुल स्क्रीन दिख रहा है।
स्लाइड शो नहीं की।
Can I start?
Yeah, please. He let him start.
स्टार्ट कर रहे हैं? दिख रहा है?
हाँ जी सर, इट्स ओके सर, यू जस्ट स्टार्ट।
नहीं, YouTube पर दिख रहा है।
Yes, sir, this is visible by clicking on.
इसको पीपीटी को भी फुल स्क्रीन कर दीजिए सर।
कर दिया मैंने, कर दिया।
अच्छा, अब वो फुल स्क्रीन पे सर अगर आप ऑल्ट टैब करेंगे तो वो आपको
Alt?
गूगल मीट वाले ऑल्ट और टैब
हाँ
एक साथ प्रेस करेंगे तो अब आपको वो 4-5 स्क्रीन दिखाएगा, 2-3 स्क्रीन जो सामने के हैं। तो जो आपका गूगल मीट वाला है उसको आप क्लिक कर दीजिए।
हाँ, ये किया है।
अब इसमें आप अपना, अच्छा उसमें जाइए प्रेजेंटिंग वाले में सर, उसको ऑफ करके प्रेजेंटिंग में जाके फिर से आप कर दीजिए तो आ जाएगा सर। ये जो दिखा रहा है प्रोफेसर घटक इज प्रेजेंटिंग।
हाँ
सर
इसमें तो लिखा है कि आई एम प्रेजेंटिंग। एक दफे और कोशिश करता हूँ।
Sir, if you click on slideshow, then it will be full screen, I think.
हाँ, so
Sir, entire screen. Select the entire screen, not the window.
can you now see the part of the screen? Can you see the slide?
Yes, sir.
Yes, sir.
Yes, sir. Please go ahead, sir.
Yes, yes, it's visible now. Okay, sir.
Okay. Thank you.
आ गया सर ये।
Thank you. I'm indeed so happy to be again participating in a seminar organized by Pandit Ravi Shankar Shukla University. I was there, as was mentioned by Professor Tiwari, 5 years back, and it was a very, very enjoyable experience. And I have prepared a talk, a small amount on Raman effect, but mainly on the fiber optics revolution. And the photograph that is there on the first screen, I have shown Ravi Shankar University, Ravi Shankar Shukla University, and a light getting guided through the fiber. The photograph shows a red laser beam guided through an optical fiber fabricated in Central Glass Ceramic Research Institute, Kolkata. If all of you would switch off your microphone, that would be good. Every year, as was mentioned by Professor Tiwari, that on 28th February, we celebrate Science Day. Why 28th February? Now read the next slide very carefully. On 28th February 1928, K.S. Krishnan, who was PhD student of C.V. Raman, observed Raman effect. He was the first to observe Raman effect in several fluids, which was called the new scattered radiation. And it was a leap year, and Raman made a newspaper announcement on 29th February. Raman effect is a scattering process. And of course, what is scattering? You see, for example, if you have a positively charged particle, like an alpha particle, approaching a positively charged nucleus, then there will be a force which will repel, and the alpha particle will change its direction. So this process, in which an incoming particle changes direction, is known as a scattering. So Rayleigh scattering can occur from interaction of light with individual atoms or molecules, like the atoms and molecules present in air. And Rayleigh scattering is inversely proportional to the fourth power of lambda. And so therefore, higher the wavelength, smaller will be the Rayleigh scattering. And in the visible region of the spectrum, the blue color has the smallest wavelength, 0.4 micron, and the red color has the highest wavelength, around 0.7 micron. And therefore, the blue component gets scattered by the molecules present in the sky. And so therefore, the sky appears blue. And the setting sun appears red in color because the blue component coming from the sun is predominantly scattered out. And so therefore, the sun looks red in color. On the other hand, if you are on the surface of the moon, then the setting sun will be completely, or the rising sun will be completely white. And the sky will be completely dark. And that is because moon has almost no atmosphere. There are no molecules there which will make Rayleigh scattering. So as I mentioned, the light that comes out of the fiber is due to Rayleigh scattering. The simplest atom, as you all know, is the hydrogen atom, which consists of a proton. And in the simplest model of the hydrogen atom, Bohr model, the electron rotates in discrete orbits. And this discrete orbits is characterized by the fact that the angular momentum is an integral multiple of h cross. And so therefore we say that the atom exists in different energy states. And when the atom makes a transition from a higher energy state to a lower energy state, it creates light of particular frequencies.
Sorry to interrupt you, but we are unable to see the slides.
Can you see the slides?
I think the slide is stuck. We can see only the one slide.
Oh my God.
Slides are not moving, sir.
तो कोई भी स्लाइड नहीं देखा?
पहला ही दिख रहा है, अभी तक पहला ही दिख रहा है.
Yes, sir, एक ही
Oh
slide
my
दिख रहा है
God.
बस.
ठहरिए. तो फिर मैं दोबारा करता हूँ. Sorry.
Sir, can you share PPT with us so that we can run from here also?
अच्छा, तो मैं आपको पीपीटी थोड़ा बड़ा है, मैं जरा मैं उसका वो पीडीएफ भेज देता हूँ.
हाँ सर.
सॉरी.
अच्छा, पीडीएफ आप नहीं चला पाओगे.
किसको? डॉक्टर तिवारी आपको भेज दें?
भेज दीजिए सर. हाँ.
Just 1 second. आपके जीमेल में एक मिनट मुझे पहले ही भेज देना चाहिए था. हाँ, भेज दिया मैंने.
यस सर.
आ गया?
नहीं आया सर अभी. आ गया सर.
आ गया.
मिलके तुमको डाउनलोड कर लो उसको, हम तुमको वो पीडीएफ वो भी निकाल भी लिया, उसको तुम चालू कर दो यहाँ से। यहाँ से कर सकते हैं ना? हाँ, यहाँ से कर लो। अच्छा आ जाओ। फुल स्क्रीन नहीं होता क्या? सर हो जाएगा सर, इसको
Can you upload this?
Yes, I have uploaded, sir.
अच्छा, वो मैंने आज सुबह एक स्लाइड और ऐड कर दिया था, तो आप वो लेटेस्ट वाला अगर अपलोड कर देंगे तो वो भी मैंने भेज दिया है, उसको अगर कर लेंगे तो अच्छा रहेगा।
नहीं, वो तो करना पड़ेगा, शेयर करना पड़ेगा। किसमें चल रहा था सर ये? इसमें लॉगिन करें। अच्छा, ये इसी में चल रहा है सर, ये उसको डाउनलोड करना है सर? इसका पीडीएफ को डाउनलोड है ना? डाउनलोड है ना सर? हाँ, तो अब उसको पीडीएफ को ना दूसरे ब्राउजर में कर लेता हूँ।
एक दफे और कोशिश कर लेता हूँ। Can you see the full screen?
Yes, sir.
Sir, can you please click on the slideshow? It's in the top.
ठीक है?
आने दो। Now at least the slides are moving. We had the second number also.
तो मैं कहता जाऊंगा, नेक्स्ट स्लाइड कर दीजिएगा।
बिल्कुल।
लेकिन ये ऐसा होना नहीं चाहिए।
Sir, in the top there's an option called slideshow.
Can you see the slide now?
Yes, sir.
And I have changed it. Can you see now? Is it changing?
Yes, sir. Now it is on full screen. Yes, sir. It is moving.
You can shift them. We can see you are shifting.
So can you see this now?
Also, it is full
Yes,
now.
sir.
Please go ahead.
Acha. So as I mentioned, can you see that every year on 28th February?
Yeah. Yes.
Okay. Every year on 28th February, we celebrate Science Day in India. And on 28th February 1928, K.S. Krishnan, a student of Professor C.V. Raman, observed Raman effect in several fluids, which was called the new scattered radiation. And Raman made a newspaper announcement on 29th February because it was a leap year. Raman effect is a scattering process. And what is scattering? Scattering is... ठीक है, scattering दिख रहा है?
No, sir.
अभी वो 2 मिनट वाला
दिख रहा है सर?
अच्छा. So here I have shown that an alpha particle getting scattered by a positively charged nucleus, and when it changes its direction, this process is known as scattering. So one of the important scattering mechanism is the relay scattering, which occur when light interacts with individual atoms or molecules. And this relay scattering is inversely proportional to the fourth power of wavelength. Higher the wavelength, smaller is the relay scattering. And as we know that the wavelength of light, the blue component is 0.4 micron and the red component is 0.7 micron. So therefore, the light coming from the sun gets predominant, the blue component gets predominantly scattered, and you can see the blue sky. तिवारी जी, blue sky दिख रहा है? तिवारी जी?
Yes, sir.
Blue sky दिख रहा है?
Alpha particle trajectory is showing, sir.
Oh my God, ये तो ठीक, ओहो, तो थोड़ा टाइम ले रहा है, थोड़ा टाइम ले रहा है.
No, relay scattering can occur.
हाँ.
Next, चलिए, next.
Relay scattering can occur, तो थोड़ा टाइम ले रहा है. Can occur from interaction of light with individual atoms or molecules. Relay scattering is inversely proportional to the fourth power of the wavelength. Higher the wavelength, smaller will be the relay scattering. अब दिख रहा है light spectrum?
No, sir.
गड़बड़ हो गया. तो आप PDF को दिखाइए.
ये PDF ही देख रहे हैं अभी ये लोग, जो हम यहाँ से चला रहे हैं. देखो कैसे चलाएंगे.
अच्छा, तो आप PDF दिखा रहे हैं?
Yes, sir.
अच्छा, तो फिर ऐसा करता हूँ, मैं भी PDF ओपन करके मैं आपको नेक्स्ट स्लाइड कर देता हूँ. ठीक है, ठीक है. Okay. Let me then show the PDF only.
PDF को अपना कैंसिल कर देता हूँ. सर, आप PDF को वहां से शेयर कर दीजिए सर.
हाँ.
हम अपना PDF बंद कर रहे हैं.
अच्छा.
आप उसको शेयर कीजिए, हम इसको लॉग आउट करते हैं इसको जो है.
अच्छा, ठीक है.
आप PDF शेयर कर दीजिए.
ओके, एक मिनट, इसको बंद कर देता हूँ. हाँ. अब PDF दिख रहा है?
Yes, sir.
PDF दिख रहा है?
Yes, sir.
Yes, sir.
दिख रहा है सर, दिख रहा है.
अच्छा, अब नेक्स्ट स्लाइड पर आ गए हैं?
आ गए. Yes.
बिल्कुल आ गए.
अच्छा, तो this is a photograph showing a red laser beam guided through an optical fiber fabricated at Central Glass Ceramic Research Institute in Kolkata. अच्छा, now every year on 28th February we celebrate Science Day in India, and that is because अब ये कृष्णन का फोटो दिख रहा है?
Yes, sir. It is perfect now.
Yes, sir.
अच्छा, so on 28th February 1928, K.S. Krishnan observed Raman effect in several fluids. So I wanted to emphasize K.S. Krishnan was the first person to observe the Raman effect, and I will tell you what the Raman effect is, which was called the new scattered radiation. Raman made a newspaper announcement on 29th February. Raman effect is a scattering process. Simple scattering is a positively charged alpha particle. When it sees a positively charged nucleus, it changes direction. So this process is known as scattering. And relay scattering occurs from interaction of light with individual atoms or molecules. And the relay scattering is inversely proportional to the fourth power of the wavelength. And therefore, higher the wavelength, smaller will be the relay scattering. And as we all know, the blue component of the visible region has the smallest wavelength, about 0.4 micron. And the red component has 0.7 micron. And therefore, the blue component gets predominantly scattered by the sky, by the molecules in the air. And so therefore the sky appears blue and the setting sun appears red. Tiwari ji, red setting sun दिख रहा है?
Sir.
Yeah, दिख रहा है.
Yes, sir. Go ahead, please.
ठीक है. लेकिन अगर आप, if you are on the surface of the moon, then the setting or the rising sun will be white in color, and the sky will be completely dark, because as you all know, moon has almost no atmosphere. And the light that comes out of the optical fiber, because of which you can see the optical fiber, is due to Rayleigh scattering. Now, the simplest atom is as you all know, is the hydrogen atom. And in the simplest model of the hydrogen atom, the Bohr model, you have a proton and electron in discrete orbits, such that the angular momentum is quantized. Now, therefore, each level of the atom is represented by a definite amount of energy. And when the atom makes a transition from a higher energy state to a lower energy state, light of a certain frequency are emitted. And that is the characteristic spectrum of an atom. This is the emission spectrum of the atom, of the hydrogen atom. And this, I'm sure all of you have read even in your school. And this is a signature of the atom. By seeing the spectrum, I can identify the atom that is present. That is how we know that what kind of atoms are present in the outer atmosphere of the sun, or for that matter, of any star. This is the simplest spectrograph. You have a discharge tube with hydrogen gas. It emits the light, the characteristic spectrum of the hydrogen atom. If you pass through a slit, and then the prism, which acts as a dispersive thing, and you observe the lines, the characteristic lines on the photographic plate. This is the simplest spectrograph. Now here, this is a molecule, a water molecule, which consists of 2 hydrogen atoms and 1 oxygen atom. Now in the next slide, actually I had shown the actual vibration. It is a beautiful animation. And unfortunately, if I had shown you the PowerPoint slide, the different vibrational modes of the water molecule, I have tried to show through an animation. So a molecule can have different vibrational modes. And each vibrational mode has a set of characteristic energy levels in the associated with the molecule. So when the light comes in, these are the energy states of the molecule, say water molecule or a carbon tetrachloride molecule. And if the light interacts with the atom or the molecule and gets excited to a virtual state and de-excites to the same state, so that this scattered radiation has the same wavelength as the incident radiation, then that is known as Rayleigh scattering. On the other hand, if the incident radiation, which I have shown in green in color, excites the molecule from a lower state to a higher state, and then it makes a transition to a higher state, so that the frequency of the emitted photon is slightly less. The photon has a smaller energy, then that is known as Stokes-Raman scattering. And the difference in the frequency will give me the vibrational energy states of the molecule. On the frequencies of these Stokes and anti-Stokes lines, you can determine the vibrational energy levels or the energy levels of the molecule itself. And there lies the tremendous importance of Raman effect, because that is the signature of the molecule. And so therefore you can obtain the structure, the vibrational spectra of the molecule itself. And so therefore on 8th March 1928, Raman communicated a paper entitled A Change of Wavelength in Light Scattering to Nature, which is supposed to be one of the best journals in physics. And the paper was published on 21st April 1928. And in the very first line, he wrote further observations by Mr. Krishnan and myself. So the experiment, as has been reported in one of the authoritative biographies of Raman, the experiments were observed, the Raman spectra was observed by K.S. Krishnan himself. But it so happened that in the first paper, Raman sent it in his own name. Many feel that it should have been a Raman Krishnan effect, or a Raman should have included, because the main observations were carried out by K.S. Krishnan. I would also like you to see that in the first paper, it was sent from 210 Bobazar Street in Kolkata. And I would like to tell you a little history about it. That in 1869, in an article on the desirability of the National Institution for the Cultivation of Sciences by the natives of India, the great visionary and philanthropist, Dr. Mahendralal Sarkar wrote, philanthropist is a person who gives away his own money for the benefit of others. Bill Gates is one of them, Aziz Premji is another, and many other people. So Dr. Mahendralal Sarkar wrote that the prevailing backwardness of the country was due to backwardness of science, and that the solution was in the vigorous pursuit of the sciences by original research. This he wrote in 1869. And today, even today, in India, there is 30% of the population is below the poverty line. And that is a staggering 400 million people. And how to remove that poverty? And the solution is still through education, science, and technology. I usually give a talk on this, that how education, science, and technology, only that, and not a large amount of money, can transform the nation from taking the poverty out of the nation. And therefore, on 29 July 1876, he founded the Indian Association for the Cultivation of Science at 210 Bobazar Street in Calcutta, supported by generous public contributions. He did not take even a single rupee from the government. He begged and he collected the money from rich people, and he was a medical doctor, he donated his own money to create this institution. And it is at this place that C.V. Raman carried out this work. Initially, he would organize lectures by people like Ashutosh Mukherjee, Jagadish Chandra Bose, Ishwar Chandra Vidyashankar, and for each lecture, he will charge 1 anna. Many young people would not know what 1 anna is. Anna is the 16th of a rupee. 16 annas make a rupee, and 4 paisa makes 1 anna. So that is the way he would raise money for promoting research. And Raman arrived in Calcutta in June 1907. He was employed. He was an accounts officer with the British Raj. And while riding a tram to work, he spotted the Indian Association for the Cultivation of Science, and there he did his Nobel Prize winning work. Why I am telling you this? Today in India, we require visionaries like Ashutosh Mukherjee, who appointed Raman without a PhD degree as Palit Professor of Physics. He saw the spark in C.V. Raman, and he made him a professor. Today we require visionaries like Ashutosh Mukherjee, leadership, because there is no dearth of bright young people in our country. And we just require leaders of the type Homi Bhabha, Meghnad Saha, Ashutosh Mukherjee, S.S. Bhatnagar, Vikram Sarabhai, Abdul Kalam, who have created a large number of institutions where young men and women can work and generate research and do science and technology. That alone can remove the poverty in our country. And as was mentioned by Dr. Tiwari, that C.V. Raman got the Nobel Prize in 1930 The discovery was made in 1928, and it was soon realized the importance of the discovery.
अबे तेल लाना पड़ेगा लेकिन क्यों डालना के लिए आऊँ
Please switch off your mic. Can you see this screen?
म्यूट कर लो यार.
Please mute your.
Please mute your mics.
सर होस्ट भी कर सकते हैं म्यूट उसको.
This is the original. This is the spectrograph which costed about 300 to 400 rupees, in which Raman did his famous experiments. Now, I would like to spend some time. Already we are a little late. Why study of light has become so important? Why study of light? This is slightly now changing the subject. UNESCO declared 2015 as the International Year of Light. Why 2015? Because in 1015, 1000 years back, Al-Hasan, who was in Mesopotamia, now in Iraq, wrote Kitab al-Manazir, which is the first book on optics. So the first book on optics was written in the year 1015, because of which UNESCO celebrated the International Year of Light in 2015. In proclaiming 2015 as the International Year of Light, the United Nations recognized that applications of light science and technology are vital for existing and future advances in medicine, energy, information and communication, fiber optics, agriculture, mining, astronomy, etc. So I have been trying to promote the field of optics and photonics, and that it should be taught to all engineering students. Suddenly, optics and photonics have become extremely important. And then in 2018, UNESCO declared May 16th as the International Day of Light. Why May 16th? Because on May 16, 1960, the first successful operation of the laser was done by the American physicist and engineer Theodore Myman on 16th May 1960. The discovery of lasers has led to tremendous benefits to society in communications, healthcare, and many other areas. And one of the main differences between an ordinary source and a laser source is the fact that the ordinary bulb emits light in all directions, and the laser emits in a particular direction. Because of this, a laser beam can be focused by a lens, let us suppose of 2.5 centimeter focal length, which is the focal length of the eye. And the area of the focused spot is extremely small. And so therefore the intensity becomes extremely high. And so therefore, even a 2 milliwatt laser beam can produce an intensity of 3 megawatt per square meter. Such high intensities will damage the retina. So never look into a seemingly innocent low power laser beam. What I wanted to tell you is that whereas it is safe to look at 1,000 watt ordinary light bulb, but it is very unsafe to look at a 1 milliwatt laser beam, because it is highly directional and therefore it can be focused to a very narrow area. Using focused laser beams, extremely important devices have been created for the industry and also defense. Here, a focused laser beam is shown as drilling through the concrete. And this photograph has been obtained from RRCAT Indore. RRCAT is Raja Ramanna Center for Advanced Technology in Indore. And Dr. Brahmanand there has been one of my former students from IIT Delhi. And here is a fiber laser cutting steel. As you all know, laser beam is extensively used for eye surgery. And one of the important application has been in laser-induced fusion. Powerful laser beams can create temperatures. You see, focused laser beams can create temperatures which result in generation of fusion power. The above photograph shows the setup at the Lawrence Livermore Laboratory in the United States. It can deliver more than 500 trillion watts of peak power to the target. So that is the greatness of the laser beam, and very soon we can have, we should have fusion reactors, and in which I mean, you can generate electricity through fusion energy. And then, in order to tell you about the importance of the field of photonics, I thought I should mention that the 2018 Nobel Prize in Physics was awarded for groundbreaking inventions in the field of laser physics. And half of the prize money went to Arthur Ashkin for optical tweezers and their applications to biological systems. At that time, Arthur Ashkin was 92 years old, and only a few months back, he passed away. He discovered what is known as an optical tweezer. What is an optical tweezer? This is an actual tweezer holding a tiny diamond. So this is known as a tweezer. And here, optical tweezer is one in which you can manipulate micron size beads or virus or something like that. I'll tell you how it works. As you all know, light can be emitted or absorbed only in discrete amounts called quanta. Einstein called them quanta of radiation. Now we call them as photons. The energy of each photon is equal to h nu. The momentum is h nu by c. And so therefore, when a light photon or a light beam, let us suppose you have a tennis ball or a cricket ball hitting a stationary train. Then, because the tennis ball will change its direction, it will impart a small amount of momentum to the train in the forward direction. So if it is on a frictionless train, then the train will start moving with this very, very small velocity. And similarly, if a light beam is incident on a mirror, then the photon changes its direction. So although the magnitude remains the same, but since the photon changes its direction, to conserve the momentum, a small momentum is imparted to the mirror in the forward direction. Very tiny amount of momentum is imparted in the forward direction. This is the principle of the optical tweezer. Now, so therefore, if you have a light beam, if you have a collimated laser beam hitting a lens, then it will focus. The beam will get focused and the beam will change its direction. The photon is moving in this direction and it will change its direction. And so therefore, it will impart a very small amount of momentum to the lens itself in the forward direction. And so therefore, here is a laser beam propagating, let us suppose, in the upward direction. The intensity is maximum on the axis and it sort of dissipates, it decreases. Sometimes mostly as a Gaussian beam, the intensity is maximum here and the intensity becomes minimum here. So there is a micron size, 10 to the power of minus 6 meters diameter about a bead here. Now, a ray of light will change direction, and so therefore there is a net momentum which will be imparted by ray 1 in this direction and by ray 2 in this direction. And so therefore there is a tiny momentum, tiny force that acts on the bead in the forward direction. Now, on the other hand, if the bead is slightly displaced from the center, then this ray is much more intense than this ray. Therefore, this force, restoring force, which will try to pull the back. So, because this ray 2 changes direction, so therefore the photon will have the photon changes its momentum, and so therefore there is a small force which is exerted in this direction. So because of this force, since the ray 2 is much more intense than the ray 1, the bead will move towards the center. So if you have a focused laser beam, and then it will trap the bead. It will trap the bead. And the main principle, so a focused laser beam is made to fall on the sphere, which in addition to keeping the bead in the center of the laser, also keeps the bead in a fixed axial position. And so therefore there lies the main principle of the optical tweezer. So if you go to YouTube and maybe right on YouTube, I wanted to show the video, but unfortunately I cannot show you the video right now. The Elliott Scientific Optical Tweezer System, and you can manipulate each micron size bead and take from one place to the other. So this is a revolution that has occurred in biology. Then Gerard Moreau and Donna Strickland received the other half of the 2018 Nobel Prize in Physics for chirped pulse amplification. And this work that they did in Rochester, and the basic principle is that you have an unchirped light pulse, you pass through a device in which the group velocity decreases with wavelength. So the pulse will broaden in time and will get chirped. But the peak power will become smaller. And because the peak power becomes much, much smaller, it can be amplified, and you have stretched chirped pulse getting amplified. And then you pass through a device in which the group velocity increases with wavelengths. So pulse will get compressed with increase in peak power. This is a very simple. It involves a little bit of mathematics, which I have now described in the latest edition of my optics book. And the technique involves taking a short low energy laser pulse, stretching it to make a long low energy pulse, amplifying it to get a long high energy pulse, before finally compressing it to get a short high energy pulse. This is a simple application of the dispersion phenomenon. It's a very beautiful application. And such ultra short high intensity laser pulses produced by the method that I have just now mentioned, chirped pulse amplification, find extremely important applications in industry. For example, in cancer treatment, in many commercial products, in eye surgery, etc. Indeed, since 2011, CPA has been used in 24 million eye operations. Let me skip this. The holography is another application of optics, quantum optics. Blue light emitting diodes, for which the Nobel Prize in Physics was a 2014 Nobel Prize was awarded. See the large number of Nobel Prizes that have been awarded in recent years in the field of lasers and photonics. I wanted to spend 1 minute on this. The 2017 Nobel Prize in Physics was awarded to these three gentlemen for contributions to the LIGO detector, an observation of gravitational waves. LIGO stands for Laser Interferometer Gravitational Wave Observatory. So it is essentially a gigantic Michelson interferometer. You have a beam splitter here, you have a laser here, and this is a 4-kilometer arm. Laser beam gets reflected by a mirror, and 1.3 billion light years back, there was a violent collision between two black holes. So it is 1.3 billion light years away. And the gravitational spheres were created, and which affected the two arms differently. And the resultant interference pattern changed, and that could be detected by this. So it is all optics. This LIGO experiment is all optics. And this is a LIGO facility in the United States. This is a 4-kilometer long arm. 4-kilometer long arm. And the laser beam travels here, gets reflected, and then interferes. And the setup is just the Michelson interferometer, which you must have read in your undergraduate class. The good news is there are 4 LIGO observatories in the world. There is one planned in India. And I hope I live to see the LIGO facility in India, which will be created in Pune. And when that happens, there will be a huge requirement of very well-trained optics engineers. And then there are beautiful experiments can be carried out with a laser. Here, red light falling on a suitable crystal getting converted to blue light. So what I have been able to, I hope I have been able to tell you that why study of light or of photonics has become extremely important, not only for students of physics, but more so in engineering. Now I spend the remaining. तिवारी जी आप मुझे कह दीजिएगा कब खत्म करना है, थोड़ा देर हो गया शुरू करने में. Whenever you want, I will finish.
करिए, कंटिन्यू करिए सर.
10 मिनट का टाइम दीजिएगा, मैं वाइंड अप कर दूंगा. ठीक है? So I will now spend the remaining period of my time on the subject that I have been very passionate about, fiber optics, a technology that has created a revolution and has made phone calls free. Now, it is because of fiber optics and fiber amplifiers that today I am now sitting in America and you can listen to me and in India, and it is almost free. It is almost free. And that has been possible because of fiber optics, lasers which can be modulated with tremendous rapidity, and also optical amplifiers. I will briefly describe them. So light guidance through the optical fiber takes place because of total internal reflection. Here is a total internal reflection of light at the interface of water and air. And so therefore, in an optical fiber, as I'm sure most of you know, light guidance takes place because the cladding is usually pure silica, SiO2. And core is silica doped with germanium. And so therefore, because of the doping, the core refractive index is slightly higher. And so therefore, light undergoes total internal reflection at the boundary of core and cladding. And that is how, very simply put, light gets guided through the optical fiber. So the core dimension is from 10 microns for a single mode fiber. I don't have the time to tell you the difference between a single mode fiber and a multi-mode fiber. And for a multi-mode fiber, this is about 100 micron. And the cladding diameter is about 125 microns. And this is the light that gets guided. Green light is getting guided. And the very fact that light comes out is because of the relay scattering that I had mentioned. There are 3 areas in which the optical fiber is playing an extremely important role. One is in image transfer, the second is in optical communication, and the third is in devices. So I will describe one each very briefly. So if you have a large number of aligned fibers, and if you have aligned fibers, this is known as a coherent bundle. So they are not jumbled up. This is the front end of the fiber, this is the back end of the fiber. So if our front end of the fiber is dark, then the dark end of the back end of the fiber is also dark. So this is a fiber bundle held by a human hand, and there can be thousands of fibers inside. And so, as you all know, it can be put inside the human body, either down the throat or through the anus, and one can see the inside of the human body. This is a stomach ulcer that one can see without opening up this stomach. So this is a revolution in medical field. And if you use a high power laser beam, then you can use one set of fibers to illuminate the ulcer and the other set of fibers to focus the laser beam and destroy the tumor or something like that. And without carrying out any surgery as such. So this technology has tremendous application as you all know, in medicine. So this is the end of the fiber bundle, and as seen through a microscope, and you can see individual fibers. These are the one end of the individual fibers. Then there is also an application of optical fiber in solar lighting, not solar energy, not solar energy. You see, these are plastic fibers. Up till now, I have been talking of glass fibers. Plastic fibers, which have a core diameter of 8 millimeter and 11 millimeter, such large diameter plastic fibers can be used to transport light from the rooftop to the room. So this technology is getting promoted by many people, and if you from the roof you collect the sunlight and transport it to the room. And so the basic principle is, this is the light coming from the sun, you collect it, and then you transport it through the optical fiber inside the room. Now, in a country like India, where in Rajasthan, Punjab, UP, Madhya Pradesh, there's a tremendous amount of sunlight. And so therefore, we can use optical fibers and the sunlight to illuminate rooms in schools and colleges and hospitals, of course, only during the daytime or only when it is not very cloudy or dark. Here is an actual illumination of a room in Netherlands. So the Western Europe have adopted this technology in a very big way. And I think I have been trying to promote the use of this technology even in India. Now I come to the last part, the optical fibers and communication. Now, here, you see, as you all know, in television, you use a larger carrier frequency than in radio. Why? Because in television, you have to transmit the images, transmit visuals, and so therefore it necessitates higher carrier frequency. So higher the frequency of the carrier waves, higher would be the information carrying capacity. And as you all know, that the entire electromagnetic spectrum, from gamma rays to X-rays to radio waves, they are all electromagnetic waves. They all propagate with an identical velocity in vacuum, 299,792,458 meters per second. But they are characterized by different frequencies. So the visible portion of the spectrum has a frequency of over 100 terahertz, and the radio frequencies can be megahertz to gigahertz. Now, light frequencies, as I just now mentioned, has a frequency of about 100 terahertz, 10 to the power of 14 hertz, which is much larger than the radio wave frequencies, which are in the megahertz region, or microwave frequencies as gigahertz region. So light waves are capable of carrying much larger amount of information. And so here, therefore, it has been always the engineer's dream to use light beams for carrying information from one place to the other. These are the bit requirements for a telephone about voice communication, 64,000 bits per second. For standard TV is 100 megabits per second. High density TV, 1.2 gigabits per second. So you have an analog signal. Let's suppose you are talking on the telephone, you digitize it. So when you are speaking, you create pulses at the coded pulse train of about 64,000 bits per second. On the other hand, if it is a high density TV, then it's a gigabit per second. And then these optical pulses are passed through a fiber link. And once this can be 80 kilometer long or 100 kilometer long fiber link, if small energy is the energy gets lowered and attenuated, the beam gets attenuated, each pulse gets attenuated. And if you are still able to resolve each bit, then you can retrieve the original signal. The two characteristics that I tried to mention of the optical fiber is the attenuation and dispersion. That is, you send a very sharp pulse, nanosecond or a picosecond pulse, it broadens in time. That is known as dispersion of light pulses. But if the dispersion is very large, then the two consecutive pulses will start overlapping. So a good communication system must have a low attenuation and must have a low dispersion. I don't have the time to talk about dispersion, but I will talk a little bit about attenuation. I must mention that the first optical communication system was set up by Graham Bell in 1880. He called it the photophone. In this system, sunlight was modulated by a diaphragm and transmitted through a distance of about 200 meters in the air to receiver containing a selenium cell connected to the earphone. So this is the first experiment on optical communication. And between 1880 and 1960, there was not much work in communication using light beams. Then, as I have told you before, a revolution occurred. Theodore Maiman fabricated the first laser on May 17, 1960. Initially, people thought that we will use open-air communication systems. But in the open air, there is a lot of dust particles and cloud, etc. So it was a very inefficient way to transmit from one rooftop to the other rooftop. In 1966, this gentleman is Charles Cow. A very profound prediction was made by Charles Cow and George Hockham of Standard Telecom Laboratory in the United Kingdom. They said that glass fibers represent a possible practical optical waveguide with important potential as a new form of communication medium. And they predicted that glass has very high loss if the tiny impurities in glass are removed and the loss is brought below 220 dB per kilometer. Now, I'm sure all of you know what is the dB. The power loss is always measured in dB, which is 10 log 10 input power by output power. So if P1 is equal to P2, then alpha is 0. This is 0 dB power loss. 0 dB power loss means no power loss. If P2 is half P1, then this becomes log 2 to the base 10, that is 0.3, so 3 dB. 3 dB power loss means 50% power loss. Similarly, a power loss by a factor of 10 is 10 dB power. It's a logarithmic scale. Power loss by a factor of 100 is 20 dB. Power loss by a factor of 1000 is 30 dB. An amplifier which has a gain of 30 dB means the power amplification by a factor of 1000. So in 1970, Donald Keck, these three gentlemen, Donald Keck, Robert Maurer, and Peter Schultz at Corning Glass Works in the US produced silica fibers having loss of about 17 dB per kilometer. The Charles Cow had predicted the loss should be below 20 dB per kilometer. And they purified glass and they used what is known as the chemical vapor deposition technology to fabricate optical fibers which have a loss of 17 dB per kilometer. By 1980, the loss was so small that this is a curve describing the loss as a function of the wavelength. So at 1.55 micron wavelength, the loss is about 0.2 dB per kilometer. Remember that the loss it should be, Charles Cow and George Hockham said the loss should be below 20 dB per kilometer. What was achieved by 1980, which was a great, tremendous technological achievement, the loss was below 0.2 dB per kilometer. And the loss, the envelope of the loss follows the Rayleigh scattering that I had mentioned, 1 over lambda to the power of 4. These peaks are due to tiny amounts of water that remain. This peak is due to tiny amount of iron and cobalt, which are very, very difficult to remove. There is a low loss window at 1.3 micrometer. So the first and the second generation optical communication systems operated using lasers at 1.3 micron. But now, almost all communication systems operate at 1.55 micron. which is 1550 nanometer. So it is really not optical, it's in the infrared region, 1550 this thing. The lowest loss of silica fibers occur at 1550 nanometer. In India, there is a company in Aurangabad which makes this communication grade optical fiber, which has tremendously small loss. And Sterlite is the name of the company. Some of you may have heard. And they are also exporting optical fibers from India. So Charles Cow received half of the 2009 Nobel Prize in Physics. And the chair of the Nobel Committee said that Charles Cow's discovery made in 1966 led to a breakthrough in fiber optics and revolutionized the way in which information can be transmitted globally. And then in 1970, there was another major breakthrough. The room temperature semiconductor lasers. What is so the optical communication system, the starting point, we say that is the year 1970. So I will conclude by giving you one application, one device, one fiber optic device, which is the optical amplifier. Now, if you have a 1 milliwatt beam, let us suppose I'm operating at 1.55 micrometer. So then the loss is about 0.2 dB per kilometer multiplied by 80, that is 20 dB, quarter dB per kilometer. So that is 20 dB loss. So a 1 milliwatt power will decrease to 10 microwatt. So after about 80 kilometers of fiber, you must increase the power level. And therefore you require optical amplifiers. And can fiber loss be compensated optically? We can have direct amplification of optical pulses by using erbium doped fiber amplifiers. Now, as you all know, if an atom is in excited state, I told this before, it makes a spontaneous emission to go to the ground state. And it emits a photon of frequency h nu, frequency nu, such that light is emitted of frequency nu such that h nu is equal to E2 by minus E1. And then there is stimulated absorption. There is light of that particular frequency can make an atom jump from a ground state or a lower state to a higher energy state. What Einstein did in 1916 was that not only there is a spontaneous emission, but light of a particular frequency can stimulate the atom from an excited state to the ground state. And the probability of stimulated emission is the same as the probability of spontaneous stimulated absorption. This is showed in his famous 1916 paper. But what Richard Tolman did in 1924 was that the process of stimulated emission will result in an amplification of the beam. In some books, it is written that one photon becomes two photons. That is not correct. That is not correct. Light gets amplified through the process of stimulated emission. This is the semi-classical model of the atom, in which the light is treated as a wave and the atom is treated quantum mechanically. And therefore, through the process of stimulated emission, you get amplification of the beam. And that is light amplification through stimulated emission of radiation. And this is what acronym LASER stands for. And as I told you, the probability of stimulated absorption is the same as the probability of stimulated emission. Normally, there are a large number of atoms in the ground state. And so therefore, there were larger number of stimulated absorption, smaller number of stimulated emission, because the probability of stimulated emission and stimulated absorption is the same. So resulting in the attenuation of the beam. On the other hand, if I somehow can create a larger number of atoms in the upper state, then there will be larger number of stimulated emission, smaller number of stimulated absorption, and therefore resulting in optical amplification. So it was Charles Townes. This is against thermodynamic equilibrium. And so therefore no one thought about it. It was in 1951, Charles Townes, who also got the Nobel Prize, thought about the population inversion, and which revolutionized science. Now, in the case of optical fiber, you dope the core of the fiber with erbium atoms. Now look at this. These are the erbium energy levels. They form bands, and if you use a 980 nanometer light, you can excite the erbium ions from E1 to E3. This difference of energy corresponds to 980 nanometer wavelength. As soon as it reaches here, it immediately, within 1 microsecond, makes a non-radiative transition to the level E2. But the half-life of this is very large, and so therefore it sits there. And so therefore if the pump power is large, then you can have a situation where the number of atoms in the level E2 will be larger than the number of atoms in E1. And you will have a state of population inversion. And this transition corresponds to 1.55 micron or 1530 nanometer. So therefore, this is the basic structure of the erbium doped fiber amplifier, which has revolutionized communication. That you have a pump laser at 980 nanometer. It couples the 980 nanometer laser to an erbium doped fiber. This creates a state of population inversion. And so therefore a signal at 1.55 micron sees an inverted medium and gets amplified. This is the basic principle of optical amplification. And when I used to teach lasers at IIT Delhi to first year or second year students, I would first tell them about erbium doped fiber and explain them the concept of optical amplification through stimulated emission of radiation. And then I will tell them the laser. Because now you have an amplifier, you put two mirrors on the sides and you will create a laser. So that is the fundamental basis of understanding the lasers. So I will first tell them erbium doped fiber, and then I will tell them you create a state of population inversion by having a pump laser at 980 nanometer. So this then a signal now at 1.55 micron. You see, this transition corresponds to 1.55 micron. So in incoming radiation, 1.55 micron, we'll see an inverted system, and in the process, it will get amplified. So these are the erbium doped optical fiber developed again at CGCRI Kolkata. They can be manufactured in India, but still the fibers that are manufactured in India are very expensive in comparison to what is manufactured in. And with these fibers, Nest in Cochin have been selling some at first, but again the numbers are so small that it cannot compete with the production in China. So this is a typical erbium doped fiber amplifier, and this is a 25-cent coin. And 25-cent coin is about the size of a 2 rupee coin, a compact EDFA manufactured by New Photon Technologies. It provides up to 40 milliwatt output power. I show this because one of our former students, Dr. Ramdas Pillai, is the president of New Photon Technologies, and he has also set up a company in Trivandrum. So such technologies have to be made in India. So this is a typical gain flattened EDFA. Now look at this. I have 5-10 more minutes. It can have a flat gain of 30 dB. That is power amplification by a factor of 10,000. Sorry, 1,000. Over the entire wavelength region from 1530 nanometer to 1560 nanometer. And so therefore, I can simultaneously amplify a large number of wavelengths passing through the erbium doped fiber. So this is a typical fiber. This is a WDM system, wavelength division multiplexed systems, in which a large number of wavelengths, around 1.55 micron, are injected into a hair-thin fiber, and they are periodically amplified by the erbium doped fiber amplifiers. And the dispersion is also compensated. I will rather not go into it. So therefore, the erbium doped fiber amplifier was commercially fabricated for the first time around 95, 96, something like that. So before that, only one wavelength could be propagated through the optical fiber. With the availability of erbium doped fiber amplifier, by 2001, 200 channels, that is 200 independent wavelengths, could be simultaneously propagated through one hair-thin optical fiber. I'll repeat, 200 wavelengths simultaneously propagating through the optical fiber, hair-thin optical fiber, simultaneously. And therefore, this increased the bandwidth, the information carrying capacity tremendously. So the price of communication started falling down. This is a remarkable thing that has happened. In 1990s or even in 1995, if I want to make a call to Bombay, it will cost me 100 rupees for 3 minutes. Now it is free not only to Bombay, but even if you have a friend in London or New York or anywhere or New Zealand, it's all free. How has that happened? That has happened because of the low loss optical fibers and the fabrication of the erbium doped fiber amplifier. So in 2001, this is a 20-year-old data, Alcatel propagated simultaneously 256 wavelength channels, 256 independent wavelengths through one hair-thin optical fiber, sending 10.2 terabits per second of information, which means 150 million telephone channels through one hair-thin optical fiber. And so therefore now you have fiber optic cables connecting the entire world. And this is it.
Yes.
हाँ बोलिए.
Sir, continue कीजिए sir. Take your own time, sir.
अरे लोग बाग चले गए या सो गए?
Already there and large number on YouTube, sir.
अच्छा.
Very interesting,
तो
sir.
ठीक है, 5-10 मिनट में खत्म कर देता हूँ. थोड़ा पानी पीते.
Sir, आप अपना समय लीजिए, sir. Take your own time, sir.
Are you sure?
Sure, sir.
अच्छा. तो ठीक है. So this is a typical fiber optic cable which is being laid between, I mean, below the sea, and every 80 kilometers there is a amplifier. There is an amplifier of the type I have shown. Even in India, most major cities, this is a little old photograph, but all major cities are now connected with optical fibers. मैं house खास में रहता हूँ, and on the curb is the fiber link, and people say that in Gurgaon the fiber has reached home. That is, through one hair-thin optical fiber you will get telephone, you will get internet, you will get television, you will get everything. The erbium doped fiber amplifiers are extensively used in fiber-based optical communication systems. EDFA was invented in 1987 by David Payne and his collaborators at the University of Southampton, and Emmanuel de Servier and his collaborators at AT&T Bell Labs. Fiber optics and development of EDFAs have made phone calls, video conferencing like this, Zoom calls, almost free. This is a revolution. And look, the advantage that India has today. I always think how to create employment. And you know, Indians have in general can speak good English. So sitting in a remote, you see, number one, in India, sitting in a place like Raipur or Delhi or Mumbai, you can teach the entire country, even the remote villages. They have internet there now, and you can educate the masses. You can have in regional languages, you can improve the skill development. Poverty cannot be removed by giving money. Poverty can be removed only through education, particularly education of women, development of science and development of technology. And look, we have now the technology in our hand, the internet, the low loss fibers. The governments before or someone had the wise decision to use this, use optical fibers in a very, very big way. And therefore, today sitting in Delhi, I can teach a course on differential equations to a small college in Chennai or Tamil Nadu or Bihar or anywhere you can think of. So it's a revolution that has happened. And India can teach the entire world. Let us suppose I have to teach a course on quantum mechanics. There is a course that has to be taught on quantum. I enjoy teaching quantum mechanics. So I can frame a course which will be of use in USA and charge money for that. So it is opening up tremendous opportunities for skilled people. So you have to develop the skill and they use the technology to earn money. And that's it. And then these are really the last few slides. The three basic components of a laser are the active medium, which is the erbium doped fiber, and mirrors at the end of the fiber to provide optical resonator, and the pump. So this is how I used to teach lasers, that you have the pump and you have this and you put mirrors. You put mirrors and you will have a fiber laser. So you increase the pump power slowly. Initially, you will get the fluorescent spectrum, the one that I had discussed earlier. That transition between erbium, that is the light that comes out is known as the fluorescent spectrum. And then slowly increase the power, and the end faces, the reflection from the end faces provides the feedback, and suddenly it will start lasing. You can show this in a laboratory. We used to show this. So in 1961, just 1 year after the first laser was discovered, Ellis Nitzer took a glass fiber whose core contained neodymium ions, wrapped the fiber around a flash lamp, and when suitable optical feedback was applied, a laser was produced. That's only 1 year after the demonstration of the first ever laser by Theodore Neumann, the first fiber laser was produced. So this is a fiber laser that is developed by, you see, the previous slide was the 2 kilowatt fiber laser cutting mild steel. It has tremendous application. And it is such a flexible device that the RRCAT has a big program on fiber laser. But I feel that there should be 10 such laboratories like that, 100 such laboratories like that in a country of 1.3 billion people. And you can do laser welding, hole drilling, I'm sure all of you are. And then, you see, in an erbium doped fiber amplifier, you have to dope the fiber with erbium. But in a Raman amplifier, you have a signal, and then you have a pump which is separated by 13.2 terahertz, which are the difference between the two vibrational states of a silicon dioxide molecule. And so therefore, you use a pump in this direction, and if the pump power is high, then through stimulated Raman scattering, you can amplify the signal. So you don't have to dope the fiber, but the efficiency is extremely small. So you get what is known as the Raman amplification. And therefore you can have also a Raman fiber laser. These are details. So in 1928, Raman and Krishnan discovered Raman effect. I always say Krishnan and Raman discovered Raman effect, which was to become a mechanism for signal amplification and optical communication over 70 years later. So, Tiwari my lecture is almost over. So I will tell you, if you have a periodic refractive index grating,
Yes, sir.
variation in the fiber itself, in the core of the fiber itself, you obtain fiber Bragg grating, and the main advantage of that is that that a polychromatic light, white light incident on that, the reflected light is monochromatic. It is white light incident, and the reflected light is of one wavelength. It's monochromatic, and therefore fiber Bragg gratings are there are very beautiful ways. You see, you put the fiber, you write a grating which reflects lambda 1. You write another grating on the same fiber which reflects lambda 2. You write another grating which reflects lambda 3. Now this, because of temperature increase or temperature change or stress change, the periodicity changes. It gets elongated. Then the wavelength of the reflected light also gets changed. So this is another area of fiber optics, the fiber sensors, which has also a revolution. So today now, in all bridges and all major civil structures, you have fiber-based devices which act as sensors of temperature and stress. There was a bridge which collapsed in the USA some time back in 2007. People say that if there were fiber sensors inside it, its health could be monitored. And so even in India, Central Grass, they measure temperature using fiber Bragg gratings inside a 400 kilovolt power conductor at Subhash Gram station, power grid compression in India, and so on. And finally, you see, therefore, if you have a albedo fiber, at the end you write two gratings. They will act as a reflector, and they will act as a seed laser. So the story goes on, and you can have Faraday rotation and nonlinear effects to produce the entire white light spectrum and so on, solitrons. Today, I got a new scientist report. Today, this is February 27, Google uses underwater fiber optic cable to detect earthquakes. So these are the references. There is a book on fiber optic that Professor Tyagarajan and I wrote. It's a slightly advanced book, but in the 7th edition of Haptics, whatever I have done today, it is all given there, including cross amplification and optical tweezers and so on. And these are some of the books that came out from our group. And some software also we wrote, and experiments and the 2 reviews. Thank you, Professor Tiwari. Thank you for all your देर हो गया.
No, sir. We enjoyed the lecture, sir. So, any questions from audience, sir? If you want to ask any question, audience, participants.
Actually, in the output end of the fiber optics, we use some mirror. You show that. What is the actual importance and use of that mirror?
Oh, the mirror is used to so that the fiber becomes a resonator. Feedback for feedback. You have to have a mirror.
Thank you, sir. Thank you.
So, what is difference between Raman scattering and Compton scattering?
Oh, Compton scattering is a change. It's just a inelastic collision. The frequency gets changed. The frequency gets changed. It interacts with a electron, and the frequency gets changed. But here in Raman scattering gives a signature of the vibrational and the rotational energy levels of the molecule. This is an interaction with the molecule itself. There, it is the interaction with a single electron, and there is a small frequency shift. That's a continuous variable. That's a continuous variable. Here you get discrete lines. And that is the consequence of the vibrational and rotational energy levels of the molecule itself. There, in Compton scattering, it is the interaction of the electron, and the beam undergoes inelastic scattering, and the scattered light is of a slightly different frequency.
Thank you so much.
Chalo.
So why is India lacking behind in production of semiconductor devices as compared to other countries?
That's a very difficult question to answer. Why we are, I mean, I don't know. I don't want you to record this, but so I'll speak in Hindi. That आज से 30-40 साल पहले हम लोग चाइना से बहुत आगे थे, और हम कहाँ पीछे रह गए. तो उसका वजह यही है कि we have not been able to provide the leadership that was necessary for because our younger generation, जो मैं सोचता हूँ, they are extremely bright, they are extremely eager to work hard. But you see, everyone asks me, India में CV Raman के बाद कोई Nobel Prize नहीं मिला. I said that it would be really good to have a Nobel Prize. But in my opinion, India needs leaders who may not win the Nobel Prize, but they will have to create infrastructure and places where young people can excel in large numbers. आज एक लेबोरेटरी में फाइबर लेजर तैयार हो रहा है, 1-2 लेबोरेटरी में. ऐसे इस कंट्री में 100 लेबोरेटरीज होने चाहिए. So it has to be. These are easy to say and difficult to do. But in China, I have visited. एक डिपार्टमेंट में 200-300 फैकल्टी मेंबर्स हैं. हमारे यहाँ अभी भी एक डिपार्टमेंट में 10-20-30 फैकल्टी मेंबर्स हैं. तो उसका एक बहुत, it has to expand in a tremendously large way, and we can do that. We have the people, we have the money का कोई वो नहीं है. But बहुत सारी यूनिवर्सिटीज हैं, कितने दिनों से अपॉइंटमेंट्स ही नहीं हुए हैं. कोई कहता है कि रिजर्वेशन के लिए नहीं हो रहा है, कोई कहता है किसी के लिए नहीं हो रहा है. एक सेंट्रल यूनिवर्सिटी है, वहां पर 50 लोगों की वैकेंसीज है, 10 लोग हैं. 10 लोग कैसे चलेगा? एक यंग जनरेशन जब तक नहीं देखेगा कि उसके पास क्या अपॉर्चुनिटीज है, कैसे होगा बताइए. तो ये तो रिसर्च तो बहुत इंपॉर्टेंट है, और गरीबी हटाने के लिए यही एक साधन है. तो हम एक नोबेल प्राइज विन करें या नहीं करें, इससे कोई फर्क नहीं. We require leaders like Homi Bhabha, Abdul Kalam, Jamshedji Tata, and S.S. Bhatnagar, Meghnad Saha, जिन्होंने इंस्टीट्यूशंस बनाए हैं, यहाँ पर हजारों की तादाद में लोगों की employment opportunities. Teaching is one such area where India can excel, and now with this technology, it's really one can do wonders. जैसे सॉफ्टवेयर में किया है इंडिया ने, इसी तरह से टीचिंग में भी कर सकते हैं. ठीक है. देखना.
Thank you so much, sir.
Sir, but India needs teacher like you, sir. because because it's a common.
हमारा innings तो करीब खत्म होने वाला नहीं,
Because I
but
am
I have
saying
enjoyed teaching. I mean,
because
और जो मैं आज कह रहा हूँ ना, वो मेरे ये this is from the inner part of my heart that I feel that we should have, as a country, we should have achieved more. Not necessarily more Nobel prizes, not necessary. That is not necessary. और मैं इस बात में बिल्कुल एम्बैरस नहीं हूँ। चाइना में कहाँ नोबेल प्राइज मिला है, कुछ
नहीं मिला था। हाँ।
लेकिन कितना आगे निकल गया, कितना टेक्नोलॉजी आगे निकल गया। ये जैसे फाइबर मैन्युफैक्चर का एक जगह है, 10 जगह होनी चाहिए। फाइबर एम्पलीफायर हम लोगों को बनाने का टेक्नोलॉजी है, लेकिन नंबर्स नहीं है, तो हम लोग compete नहीं कर सकते, वो तो नंबर्स आने चाहिए।
Yes, sir, yes. Because this is a common experience of students कि when they were at school and they were taught कि sir C.V. Raman won the Nobel Prize on National Science Day, and when they asked their teacher, their physics teacher, कि what exactly this Raman effect is, so they said कि the teacher thought of them, and they said it's a very very complicated. So this is a common experience the student tell. They were wondered why this complicated discovery without an obvious use had won the Nobel Prize. So today you have explained a very nice manner what is actually a Raman effect. And your talk is very relevant to the theme of the National Science Day, the science, technology, innovation, and education, skill and work, importance of education, skill and work. And because we are moving to 5G now, so the fiber optics is a gateway to our 5G, our smart cities, our self-driving cars, Internet of Things, virtual reality. So that's why this talk was very important. And you have nicely explained the Raman effect, nicely explained the EDFA, nicely explained the Raman fiber amplifier. So you're outstanding, very excellent. If any more question is there, you can ask. Participant can ask. Yeah.
Yes, sir. There is one question. What is surface enhanced Raman scattering, and what is the difference between surface enhanced Raman scattering and Raman scattering?
Raman scattering and
surface enhanced
Hello?
Raman scattering.
Raman scattering and
Raman scattering.
I wouldn't know.
Surface enhanced Raman scattering, sir.
Surface.
I would not know that. I really would not know that. What is enhanced Raman? I know only simple Raman scattering. Raman scattering is because of the vibrational levels and interaction of light with the vibrational levels of the molecule. Enhanced Raman scattering, I'm sure there are many. I'm not an expert on Raman scattering. I just know the basic principle of the Raman process. Chalo, yahi par khatam karo.
Professor Sanjay, shall I make a comment?
Yeah, sir. Thank you, sir. You're welcome, sir.
Professor Ajoy Ghatak, are you able to hear me? I'm Yakmi.
Yes, I am. Yes.
Okay. First of all, it was an excellent presentation. I would
thank
say,
you.
Bhishon bhalo. It was very refreshing and also told to the students in a manner in which they will go along with you. I have two minor comments. First comment is building on what you said and what Professor Sanjay Tiwari said just now. That school children, they get bewildered because they don't get the right kind of replies when they ask their teachers. Maybe the fault is not exactly here or there. I would say, I want to tell all the participants, most of the time, the nicest things are the simplest things. It is the simplicity of the Raman effect apparatus. School students should be taken on tour to Indian Association for Cultivation of Science, which was established by Mahendra Lal Sarkar, which Professor Ajoy Ghatak said. And how many people really know who was Mahendra Lal Sarkar? I think we have to rub it in. So similarly, I tell people, even when I go abroad, I tell you, look at that apparatus with which Raman and Krishnan made that discovery. So simple. If you look at it, You think एक लकड़ी का डब्बा है, उसके अंदर कुछ लाइट आता है. It is so simple, and children will think I could have done it. So, I mean, we have to teach them the beauty of these simple things, which can take you to the highest levels. Similarly, high TC superconductors, just some ceramic powder leke, they got a Nobel Prize. And lastly, I would say, if the children or anybody, they are in the United States, if you can go to Bell Labs, look at the original transistor, 3-legged thing. Oh, it looks miserably simple. You will just say, isko mila, right? The contact, a jump clip. You go and see that. A clip, wire nahi mila to clip laga diya udhar. Because they had the strength of the idea with them. The simplicity of the apparatus or the device is not that important as the idea to move the nation. Lastly, I would like to repeat what Professor Ghatak said. The countryside, our rural regions, already the use of the optical fiber to bring light, natural light into the वो जो गरीब लोग के झोपड़ी में लाता है दिन में, if अगर sunlight है, already this is being done, and in the other parts for the night purpose they have solar panel, so which will so this is being done. And there are many more things being done, but I think we have to go on propagating this. I think if governments will never do, colleges will never do, big scientists also will never do. Let us excite the young minds. Thank you.
Yes. बस एक चीज मुझे कहना है, जैसे आपने कहा था ना कि the younger students, if they are still there, if they have a question like the enhanced Raman scattering or Raman scattering, what technology has provided us is that if you write what is Raman scattering on the Google, then you will get 10 different answers, and you can choose the level at which you want to have. What is erbium doped fiber amplifier? If anyone wants to know, there will be 10 such things. So knowledge has become free, and you see, and Google and these things have provided us with such enormous information that if a student does not get satisfied, for example, I myself did not know what is enhanced Raman scattering, so she has to just write enhanced Raman scattering on Google and get most probably get the answer.
What a powerful medium they have now. We wish
that's right.
Old people.
And it is available. It is available to the rich, to the poor, to person in village, and this thing. And provided you have internet, और जैसे तिवारी जी एक चीज कहना है, वो शुरू में जो हमारा प्रॉब्लम आ रहा था ना, वो बैंडविड्थ का प्रॉब्लम आ रहा था. जैसे पीपीटी के लिए वो नहीं, because PPT was a 40 megabit MB system, और ये 8 MB था, इसीलिए ये
that was a problem. Yes sir.
इसको आपको इम्प्रूव करना है.
Yes sir. Yes sir. Sure sir.
घटक साहब, उसका मेरे पास एक टेम्पररी इलाज होता है आजकल. Because you have Zoom, you have Google, you have WebEx, so many systems, and when somebody invites me, you give this in the learning. But in order that I do not make some mistake, I normally have, we are all sitting at homes, I have a grandchild or somebody write with me in the initial moments, but I can't fix in 10 minutes, do it in 10 seconds. We are learning slow. They learn very fast. I'm telling you, they learn very fast. Thank you.
Okay.
Thank you.
So let's us thank Professor Ghatak. So words are not enough, sir, to express my gratitude. But I express our sincere gratitude and appreciation towards you for this outstanding and inspiring presentation. क्योंकि आपने इसमें आगे स्किल से हाउ कैन दे गेट जॉब्स आल्सो इन ऑप्टिकल कम्युनिकेशन ये भी आपने काफी उसमें तो योर सब्जेक्ट वाज वेरी रेलेवेंट टू द theme of the National Science Day of this year. So
क्योंकि उसका वजह ये है तिवारी जी उसका वजह ये है कि आजकल सब अच्छे जो स्टूडेंट्स हैं वो साइंस नहीं करना चाहते हैं एंड अब सॉफ्टवेयर करे तो भी बेटर है लेकिन अगर वो मतलब सिगरेट बेचे तो मुझे आईआईटी के बच्चे करके एमबीए करके दे आर इन बैंक्स एंड तो मुझे बड़ा कष्ट होता है बड़ा कष्ट होता है तो क्योंकि so I am trying my best to tell that there are opportunities अगर तुम फिजिक्स और मैथमेटिक्स अच्छी तरह से करोगे तो उसमें भी बहुत opportunities है. Let me tell all the younger people here.
Yes, sir.
I am 81. Even at this age, if I want, I can earn as much money as I like by just teaching. नहीं really. तो अगर आपके concepts ठीक हो, अगर आप clarify कर लें, and if your English is reasonably, आप हिंदी में भी पढ़ा सकते हैं, तो people can earn a large amount of money because people who are good in engineering and in physics or in mathematics, when they join, मुझे बड़ा कष्ट होता है देख करके कि वो विस्की बेच रहे हैं कि कोका कोला बेच रहे हैं कि and they are not happy in that. जो हम लोगों को खुशी मिली है रिसर्च करके साइंस थोड़ा बहुत रिसर्च करके टीचिंग करके जिंदगी भर कि आज तो माय सन सेज इस उम्र में भी पढ़ाना चाहते हैं आई सेड यस बिकॉज़ आई एंजॉय इट सो दिस इज so I want to put forward to the younger generation that even in basic science, if you take it very seriously, then there is lot of opportunities, lot of wealth, and wealth has become very important in today's society. That is also necessary, and you will be in a profession where you will enjoy and doing more and things like that. चलो खत्म करते हैं हाँ चलो conclude कर लो
okay so
sir I have one question. It's not a question, actually it's a suggestion. Can you please upload some kind of this kind of lectures in YouTube so that
sure.
we can able to watch.
We have recorded.
Not about this lecture, sir. Actually, I have seen some of the NVTA lectures in quantum mechanics by Ajoy Ghatak, sir. So similarly, if sir can upload this kind of lectures, so that can that you expect more from Ajoy Ghatak, sir, so that ordinary students can also access it.
Thank you, sir. Sir, actually, when I floated this circular, the brochure, I got phone from several faculty members, senior faculty members, कि अरे हमारे गुरुजी आ रहे हैं तो हम तो गुरुजी को सुनना है और I got from 5 or 6 persons here. तो घटक सर का नाम तो बुक के साथ ऑप्टिकल इलेक्ट्रॉनिक्स और आपके लेजर जो है सभी लोग जानते हैं सर. तो we are thankful sir you have spared your time and your presence itself is a source of inspiration for all of us. So we are thank you towards you, sir, and we are thankful to Dr. Yakmi sir also. We are going to organize a talk by Yakmi sir on 17th of March. Sir, we are thankful to you for sparing your time, Dr. Yakmi. And finally, we are thankful to obviously our Vice Chancellor. He is always agreed to organize such programs, the public outreach platform. The director, Professor Ghosh and Professor Pandey, our registrar, they are always with us with solutions and timely support, and Professor Balwant Thakur, who provided IT support for this program, sir. So we are thankful to all the faculty members from several NITs, Dr. Ayush Kar is there, from Jabalpur, Professor Kataran. So many professors I can see are there on the list. They have participated in this program. So thank you to all of you. Okay. So thank you, sir. Thank you very much, sir.
Thank you.
Thank you. So we are ending this, and we will upload this lecture on YouTube, and we will send you the feedback form and the certificate for the participant who registered for it. Okay. Thank you very much, sir.
Thank you.
Thank you, sir.
Thank you, sir. 88 लोग अच्छा ना दे
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
धन्यवाद सर.
Thank you, sir.